Let's talk a bit about similar triangles. What does it mean when two triangles are similar? Well, it means that they have the same shape, essentially, but potentially they have different sizes. They also have equal corresponding angles, and corresponding sides are in the same ratio. So if that all sounds confusing, let me show you what I mean. You could draw a triangle, something like this, and you could have angles A, B, and C. That would make this side A, side B, side C. That's normally how we label our triangles, right? With capital letters for the angles and lowercase letters across from those angles to represent the sides. That triangle, you could say, is similar to this triangle, which looks exactly the same as this, except it's much smaller, right? You could have, these angles would be exactly the same, right? This is angle A, this one's angle B, that's angle C. I'm just writing those letters on the outside because they won't fit on the inside, but the angles are exactly the same, right? Now your sides will be smaller, like call that side X, Y, and Z. So the sides will be smaller than these sides, but the angles are all exactly the same, right? This triangle is just a shrunk down version of this triangle, or this triangle is a scaled up version of this one. You can think of it that way. And so if all those angles are the same, that means these are similar triangles, right? And if A is, let's say, twice as long as X, that means that B has to be twice as long as Y, and C is twice as long as Z. So they have that relationship, right? You could also say that the relationship between A and B sides is the same as the ratio between X and Y, just as an example, right? Because again, these two triangles should be in the same proportions to each other. So let's look at something else here. If you have a triangle that looks like this, and we'll say that this here is 30 degrees, and this length is 5, and this length is 10, and say that's all you know about it, right? And let's say you're told it's similar to this triangle over here. So these triangles are the same shapes, right? This is also 30 degrees. This length is 2, this length is 1. You can confirm that these two triangles are similar because you have a side, an angle, and a side over here. And over here you have a side, an angle, and a side. And what's special about this is that the angles are the same and the sides are in the same ratio, right? 10 is twice as big as 5, and 2 is twice as big as 1. Therefore, with that information, you can confirm that these two triangles are similar. And so the method we're using, I guess you could say, to figure out that these are similar is called side, angle, side, because you have a side, an angle, and a side, right? Side, angle, side, right in a row, just like that. Okay? There's another way to confirm, and it's called AA, or angle, angle. And so this would work if you have a triangle like this, where you're told that this angle is something like, 40 degrees, and this one you could say is 60 degrees, again, just an example, and you're told that's similar to this bigger triangle, where this is also 40 degrees and this is also 60 degrees. So if you're given two angles in a triangle, and you're given two angles in another triangle, and those angles are the same, then using this method you can also confirm that these triangles are similar, right? There's no way that these triangles can't be similar to each other. Or there's no way that these triangles aren't similar to each other. There's one other way to confirm, and it's called SSS, or side, side, side. So, for example, if you have a triangle like this that has side lengths 10, 30, 20, that's going to be similar to a triangle that has side lengths 1, 2, and 3, because these side lengths are in the same proportion as these ones, right? You could multiply each one of these sides by 10 to get each one of these sides over here. So this triangle is just a scaled down or shrunken down version of this triangle here. So those are three methods you can use to just confirm that two triangles are similar to one another. Now we also have what's called congruent triangles, and let me write that out for you. Congruent triangles. What does it mean if two triangles are congruent? Well, you can think of it as two triangles where one of them has just been translated or rotated or reflected, right? So it's the same as the other one, except it's been moved or spun around or flipped upside down or something like that, right? So an example of this, just to make it clear, would be if you have a triangle like this where we have angle A, angle B, angle C, and therefore you have sides A, sides B, side C. That's congruent, and you use this symbol here to show that they're congruent. That's congruent to this triangle where this here is angle A, this is angle C, this is angle B, whoops, this is angle B, and this is side B, side A, side C. These triangles are exactly the same. Obviously not the way I drew them because it's not perfectly to scale, it's a little messy, but if you can imagine, these two triangles are exactly the same, except this one has been flipped upside down, it looks like, right? Like this side B used to be on the bottom, now it's on the top. So if you flip this upside down, you would get this triangle. So the sides are the same, and the angles are all the same. The only thing that's different is the position of the triangle. It's either been rotated or reflected or translated, right? Like moved in a certain direction. So if that's all that's changed, then you can say that the two triangles are congruent. And there are some ways that we can confirm congruency, right? For example, if I have a triangle like this, and the sides are 1, 4, and 5, that will be congruent to a triangle that looks like this. So similar, but this is 1, this is 5, this is 4. So it's the same positioning, right? Like the sides are the same lengths. The only thing is I've spun it a little bit in this direction. I think you could see that, right? This 5 side used to be kind of on an angle, now it's straight up and down. So I've just rotated the triangle a little bit. And because of that, it's still congruent, right? These two triangles are congruent. And so that method is SSS. If you have all three sides, then you can confirm that it's congruent if all the sides are the same. The next method is ASA, angle side angle. So if you have a triangle like this, where you have, say, this angle here we'll call 30 degrees, this length is 2, and this angle is 60 degrees. So angle side angle. That is congruent to, let's say, a triangle that looks something like this, where this is 30 degrees, this length is 2, and this is 60 degrees, right? It's the exact same triangle, it's just been rotated a little bit this way, right? So if you have an angle, and then a side next to that angle, and then another angle on the other end of that side, and you have that in another triangle, same values, then you can confirm that those two triangles are congruent. They're the exact same triangle, just rotated or changed a little bit. Okay, let's look at another method that you can use. This one is called SAS, so side angle side. Last one was angle side angle. So an example of this would be if you have a triangle maybe like that, where you have a length of 1, a length of 4, and this is 20 degrees. If you have something like that, that would be congruent to a triangle that maybe looks a bit like this, where this is 20 degrees, this is 4, this is 1. So I just flipped this triangle and also kind of reflected it, right? But as long as you have a side and then an angle and then a side in that order like that, and you have it here as well, that confirms that these two triangles are congruent. There's just been some reflections and rotating going on. Okay, let's look at another method. We have AAS, so angle, angle, side. So what that means is that you have two angles, like we'll say this is 50 degrees, and we'll say this over here is 10 degrees. And then you have another side, right? So angle, and then a side. So we'll call this side length 5. That's congruent to the triangle that looks like this, where you have this angle here is 50, this angle here is 10, and this side up here is 5, right? So you have that side attached to an angle, and then you have the next angle, right? And so if you can see that those positions are, all the same, like this is the same. You have 5 and then 50, and then over here 10. You have 5 and 50, and then over here 10. So with that information, you can also confirm that these two triangles are congruent. All right. There's one more that we can use, and it's called RHS, which means you have a right angle, you have a hypotenuse, and you have a side. So an example would be something like this. So it's a right angle triangle. You have the length of the hypotenuse, which is just the length of the side across from the 90-degree angle. And then you have another side, like this one, we'll call 10. That would be congruent to this triangle where this is 90, this is 10, and this is 12. These two triangles would be congruent. So if you have a 90-degree angle, you know the hypotenuse and you know one other side, every other triangle with those same values will be congruent to it. Let's do a word problem. Let's say you have a tree. Let me draw a tree like this. Kind of like a evergreen tree, something like that. Okay, and this tree casts a shadow. So we'll say this is your shadow. Maybe it goes a little further. Maybe it goes like that. So the shadow goes to here. And we have a guy, we'll call him Bob. He's standing over here. And he also casts a shadow, right? He's casting a shadow. Looks kind of like that. That's Bob's shadow. Okay. Now, we're told that Bob knows that he's 6 feet tall. So, okay, this here, that's 6 feet. He's 6 feet tall. And he measures his shadow to be 10 feet long. So, his shadow length is 10 feet. Okay, so we're also told that. Then it says that Bob is going to measure the shadow of the tree, and he measures the shadow of the tree to be 60 feet. The question is, based on all this information, can we calculate what the height of the tree is? This is actually pretty useful because to measure the height of a tree that's really tall, you might not be able to measure that, right? You can't get a ladder and a measuring tape and measure how tall it is. But if you know your own height and your own shadow, and then you measure the shadow of a tree, you might be able to figure out the height of the tree using similar triangles, right? Because if you notice, this situation here makes a big right angle triangle, and Bob over here, with his shadow on the ground, also makes a right angle triangle. And because the light source that's creating these shadows is presumably the sun, it's applying light at the same angle for both of these. And so these two triangles should be similar triangles. And so what that means is the ratio between these two sides should be the same as the ratio between these two sides over here. Right? There's a couple different ways you can do this, but one way would be to say, okay, the ratio between h and 60, right, the height to the base of that triangle, is the same as the ratio between 6 and 10, right? Bob's height to the length of Bob's shadow, just like that. And then you solve for h, right? You multiply both sides by 60, so you get h is equal to 60 times 6 over 10, which if you simplify that, you get 36 feet. Therefore, Bob was able to figure out that the height of the tree, despite not having a ladder, he was able to measure the height of the tree, or figure it out, to be 36 feet tall. Another way you could have done this is you could have compared the heights of the tree and Bob. So you could have said, you know, h over 6, so the height of the tree compared to the height of Bob should equal the length of the shadow of the tree compared to the length of Bob's shadow. Could have done it that way as well. Multiply both sides by 6, you get h equals 6 times 60 over 10. And if you calculate that, you're going to get the exact same answer, right? 36 feet. So it doesn't matter how you choose to compare these, as long as you're comparing things that you're allowed to compare. Hopefully that makes sense.